In section 3.6, the chain rule, we're going to learn about a certain rule for derivatives that allows us to take the derivative of composite functions. So this rule, again, is to allow us to take the derivative of composite functions. Us to take the derivative of composite functions. So maybe just a quick little review about composite functions. Let's consider a simple example, something like cosine squared of x. And this will also give me a moment to remind us notationally what this is equivalent to. So there's two functions here. There's the squaring function that is actually going to be considered the outer function. Then there's the inner function, cosine of x. So again, what we could think about, what is the outer function? The outer is going to be the function x squared, and then the inner function is going to be the trigonometric cosine function. And then again, remember the composite. If we were to think about this in terms of, let's say, f and g, so the outer is going to be, let's just call that f, and then the inner will be g. What we have right here is that the outer function comes first in our composite notation. So this is just going to be f of g of x. Or you could think about this equivalently as f as the outer function, and then inside of f we have plugged in g. So all of these are equivalent in terms of their notation, but this is something that we're going to have to get comfortable with, decomposing some function into its outer function and inner function. So that's the prerequisite skill for this section. Let's go ahead and start building the intuition about how the chain rule works and how it is related to multiple functions. So we have this fun little scenario right here, a race. So recall that the derivative is a rate of change. In a race, Usain Bolt is traveling twice as fast as a train, which is going 3 times as fast as a horse. So let's go ahead and consider Usain Bolt. We'll just do U right here. And we're told that he's traveling twice as fast as the train. So let's just go ahead and consider this, this right here, T, the train. So what we're given right here is the change in Usain Bolt with respect to the train. Well, this is just going to be twice as fast. We also have another scenario right here where the train is going 3 times faster than the horse. So let's just call this H for horse. Let's use a capital letter just since we've been using capital letters. So what we're told here is that the rate of change of the train with respect to the horse is 3 times faster. And what we're ultimately going to be asked about is how much faster is Usain Bolt traveling than the horse? So in other words, we're asked for the rate of change of Usain Bolt relative or with respect to the horse. So there's some kind of intuition here. If you kind of look at what we're given dt dh and du dt. Well, derivatives aren't necessarily fractions. We'll think about them as differentials and fractions a little bit in section 3.11, but there is some intuition to be gained by thinking about them as fractions. Notice that if we take dt dh and multiply it by the du dt, we have a cancellation that occurs between the du's and what we have, this should be du dt, dt th. Oh, that's not what cancels. We have the cancellation between the dt's, and that's where we could get this du here, dh here, and du here, and dh here. So you can see that for the chain rule, there's going to be some sort of multiplication involved in the chain rule. So to figure out what these derivatives are and what these values, to see what these values are in terms of their functions, let's go ahead and maybe drop this scenario and just think about this in terms of x and y's. So multiplication is involved. So just again, to make it clear, the chain rule allows us to differentiate composite functions. So in the following example, we're asked to go ahead and find dy dx. So just considering this as the derivative of y with respect to x, writing this with that same kind of principle as above, what we're going to go ahead and do is consider dy, the derivative of y, with respect to some u, where u is actually going to be the inner function. So we'll kind of bring that context in a moment. And then we're going to multiply that by du dx. So you can see right here we have a function y, which is a composite function. 3x squared plus 1 is our inner function. And then we have our x squared as the outer function. So we break that into the inner and outer function, and we do a little change of variable right here. So you can see right here, what we'll do is take y, and we're going to set it equal to u squared. And you can see that u squared, that u is just going to be a separate entity or variable that represents the inner function. So then we have u is going to be some other function, and we'll have this as 3x squared plus 1. So if we look at dy du right here, what we're asked to do is find the derivative of y with respect to u. So u is acting as our variable, so we're going to consider u squared, and then we'll multiply that by the derivative of u with x acting as the variable. So this is going to be the 3x squared plus 1. So when we take the derivative of u squared, we get 2u, and then we multiply this by the derivative of 3x squared plus 1, which is going to just be 6x plus 0, but we won't bother writing that 6x. And then the thing to remember is we want our original derivative to be in terms of x. So to do that, we want to go ahead and fix this substitution. So we have 2, but remember u was just a placeholder for our inner function, which was that 3x squared plus 1. And then we're still going to multiply this by 6x. So we have a little bit of cleaning up to do right here. So if I were to go ahead and multiply the numbers outside, that's going to be 12x times 3x squared plus 1. So we ultimately end up with 36x cubed plus 12x. So what we just did here was the substitution method for the chain rule. So it builds some intuition in terms of the inner variable or the inner function being basically a variable, and making that variable a substitution for the outer function, just consider the product of two derivatives. But I think it's sometimes a little bit complicated in terms of the setup. So let's go ahead and just consider another approach. And the second approach that I choose is sometimes referred to as the inside-outside method, or the technically I should say outside-inside rule, because we deal with the outer function first. So what I'm going to go ahead and do is I'm going to go ahead and just write this function down the same way. We have this y equal to the 3x squared plus 1 all squared. So realize that our outer function is just going to be the x squared. So I'm not going to necessarily think about it in terms of u. I'm just going to say, okay, my outer function is going to be x squared. And I want to go ahead and find the derivative of the outer function. Well, that's 2x. And then I'm also going to identify the inner function. The function that is plugged inside of x squared is the 3x squared plus 1. And the derivative of the inner function, or I'll just do dinner for short, makes me hungry, okay, is just going to be 6x. So with that kind of setup, I kind of have all of the variables I need, and what I'll do to find the derivative y prime is I'm going to take the derivative of the outer function, so that's going to be 2x, but instead of x, I'm not going to put x, I'm going to put the inner function exactly as is. So notice if you just kind of thought about this as x and that as x, the 2 came in down in front to give us the power rule, and that's appearing right there. But then we're going to have to go ahead and multiply it by the derivative of the inner. So again, you can see that we essentially have the same thing that we had earlier right here. Again, we'll simplify this just to go ahead and get it to a simplified form. So you would have that 12x, and then you would still have the 3x squared plus 1. So you end up with 36x cubed plus 12x. Notice we get the same thing. Again, this is the outside inside rule or method. So this is my preferred one. It just has a little bit of a cleaner approach. So let's go to the next page where it's stated formally, and then we'll just do several examples throughout this lesson. So the outside inside rule. If we're given a composite function, then the derivative of that function is the derivative of the outside, keeping the inside alone, and then multiplying it by the derivative of the inside. And again, this is stated in words. If it says differentiate the outside function and leave the inside alone, then multiply by the derivative of the inside function. So we're just going to do several examples. My recommendation is before I start every example, pause the video and go ahead and see if you can make any progress towards the solution. So if you think you got it, go ahead and pause the video and see if you can do number 1. If not, that's okay. I'm going to still provide a walkthrough. So I'm going to color code the first few problems as we get the hang of this. So right here in green is our outer function. This is a power function. Namely, it is just going to be, I'm going to just do out for short, it's going to be x to the 5th. And then the derivative of our outer function is going to be 5x to the 4th. Then the inner function is going to be 2x plus 1. So I'm going to just write this. Our inner function is going to be 2x plus 1. And therefore, our derivative of the inner function is just going to be 2. Plus 0, but of course we'll just write this. So if we want the derivative of y, what we're going to go ahead and do is we're going to take the derivative of the outer function, leaving the inside function alone. So it's going to be 5 will come down, and then we have a parentheses, and then we have to the 4th power. I'm going to need some room, so let me slide this over here just a little bit. And let's leave the inside alone. So that's 2x plus 1 just comes right down. But then we have to multiply it by the derivative of the inner, which is going to be 2. So y prime here is just going to be 10, 2 times 5, times 2x plus 1 to the 4th. Remember, do not distribute this because the 4 is locking the parentheses right here. Granted, we technically didn't need this rule. We could have FOILed this out 5 times and ended up with the same thing after some factoring, but you can see that it really is beneficial to go ahead and just work with the chain rule. All right, let's try number 2. So it's very similar compared to the last one, so I would encourage you to pause the video and try it. Here's the explanation. The outer function is going to be another power function. So it's going to be x to the 9th. So the outer function is x to the 9th. The derivative of the outer function is the inner function is going to be 4 minus 3x. So I'm going to just note that off to the side, 4 minus 3x, and I'm going to take the derivative of the inner function right here is minus 3. Now let's use the chain rule. Y prime is equal to, okay, derivative of the outer, 9 comes down. It's now to the 8th power, but I leave the inner function alone. So it's 4 minus 3x right here. And now I multiply by the derivative of the inner, which is just going to be minus 3. A little bit of cleanup. We find y prime is equal to minus 27 times 4 minus 3x to the 8th. In number 3, we're going to introduce something a little bit more complicated in terms of the inner function, but these should all be familiar based off of what we already know from section 3.3. My recommendation when you're given things like with this fraction or a rational function is just take one step and do a quick little bit of algebra to put this in a form where you could more readily apply the derivative. So this is the constant multiple rule, so that's 1/8 x squared plus x minus x to the minus 1, all raised to the 4th power. So now that I have that, I may be able to more easily identify that my inner function and my outer function are, let's start with the outer. My outer function is this quintic function, so the outer is going to be x to the 4th. The derivative of the outer is going to be 4x cubed. Then I'm going to go ahead and actually use this one right here. So that's going to color code to green. And the inner function, let's go ahead and change that color, will be represented by red. So the inner function is going to be 1/8 x squared plus x minus x to the minus 1. So the derivative of the inner function is going to be, so this 2 will come down right here, and then you'll have 2/8, but that'll just be 1/4. So this will be 1/4 x squared, or not 1/4 x squared, just 1/4 x, or x over 4, plus 1 plus x to the minus 2. The double negative makes it positive. So the derivative, y prime, is equal to derivative of the outer, which is 4 times leaving a spot to put the inner to the 3rd. So then we'll just kind of bring this inner along. So this is just going to be 1/8 x squared plus x minus x to the minus 1 times, in parentheses, I'm going to just put this in parentheses so that you realize that it's not just the x over 4 to be distributed, but that whole quantity. So this is x over 4 plus 1. And then technically we should be matching forms. So this would technically go back to the to the x squared over, no, let's see. That would be 1 over x squared if we were matching forms in terms of what we started with. So that's running together a little bit. So let me just maybe slide this down out of the way. But there is the derivative of our given function. Not a whole lot to clean up. I mean, I guess you could distribute the 4 over this one if you wanted to, but it's really fine there. All right, so number 4 now is going to have the initial algebraic step first, where we're just going to write our outer function as a power. So we'll have in parentheses to the 1/2 power because it's the square root. So let's just actually start color coding this here. So we'll have our outer function is x to the 1/2. So the derivative of the outer is going to be 1 over 2 square root of x. Again, we run into that one quite a bit, so you may just want to have that one committed to memory. Then our inner function is going to be 3x squared minus 4x plus 6. So just to have that for reference, I'll do this off to the side. The inner function is 3x minus 4x plus 6. So then the derivative of the inner function is going to be 6x minus 4. So with the setup done, let's go ahead and take the derivative. So y prime is going to be equal to the derivative of the outer. So this is going to be 1 over 2 square root of x, but again, it's not x, it's just going to bring the inside along. So the 3x squared minus 4x plus 6. And then we'll multiply it by the derivative of the inner, which is going to be 6x minus 4. All right, so again, this is the chain rule, but we can go ahead and do a quick little bit of cleanup. So the next step, I'm going to go ahead and just put this 6x minus 4 on top and realize there's going to be some cancellation with the 2. Let's go ahead and just do that in 2 steps, actually. So this is going to be 6x minus 4 divided by 2 square root of 3x squared minus 4x plus 6. And remember that technically you could think about this as being factored out, and this will be like 3x minus 2. So you could think about that like so. And then the 2's will cancel. Or you could just think, okay, both of these divide evenly by 2. So that will cancel and be left with 1. That'll be left with a 3. That will be left with a 2. So y prime is equal to 3x minus 2, all divided by the square root of 3x squared minus 4x plus 6. All right, so those are some basic examples. Let's go ahead and look at something that's other than power functions. So we have trigonometric functions and exponential functions down here. So let's, I would encourage you just to pause, try these, see what progress you can make, and then hear the solutions should you need them. If you need the answers without the explanations, just for quick reference, you could always find that on the on MyFire. All right. But here we go. So maybe just so I don't run into it as much, like as I write, I'm going to just kind of identify the inner and the outer down here below. So the inner function is going to be the tangent function. And then the outer function is going to be the secant function. And as you get the hang of this, you hopefully won't have to go ahead and kind of set this up every time. So our outer is going to be, just to be consistent, I'll just do out. So our outer is going to be, how am I doing this? Oh, let me change my color coding just to match it from earlier. So we've been doing green as our outer function. So secant will be green, and then we've been using red for our inner function. So let's just be consistent. So our outer is secant of x, and its derivative is going to be tangent. Is it going to be tangent squared? No, it's not. It's going to be secant tangent. So it's going to be secant of x times tangent of x. Then we have our inner function, which is plugged in to the secant. And remember, like every trigonometric function needs an input. So really what we have right here is secant of x, but instead of x, we have tangent. So the derivative of the inner function is going to be secant squared of x. Okay, so this one's going to feel a little bit different because the derivative has two x's. So the derivative y prime is going to be secant, the derivative of the outer, so secant of x times tangent of x. But again, I did not write x in there because it's not x that's in there, it's whatever the inner function is. So tangent of x goes in there twice. Then we multiply it by the derivative of the inner, which is secant squared of x. So that's all there is to that one. Remember, do not distribute this. This is not multiplication. That's just an example involving the derivative having more than one input, which is interesting because something that had one input ends up with two inputs in its derivative.